Greetings and welcome back. Today we're going to be looking at an introduction to NMR. NMR is a type of spectroscopy that is called nuclear magnetic resonance spectroscopy. The magnetic resonance is also used for magnetic resonance imaging, which is MRIs. So it's the same technology that medical doctors use for MRIs. We use on small molecules, and we call it NMR. The way that MRI and NMR work is quite technical, both from a math and a physics point of view, but I'm going to give you a very brief introduction into how it works and how we can interpret these spectra. And we'll talk more about the specifics in lab this semester. Alright, so any nucleus of an atom with an odd mass, that is to say a mass of 1 or 3 or 5, etc., has a spin. So if this is a little nucleus, remember the nucleus is the center of the atom, the electrons are around it. What happens is one that has an odd mass is going to spin around in a little circle. So think of it kind of like Earth. It spins around in a little tiny circle. When it does that, it generates a small magnetic field. The magnetic field, in this case, would look like that. So it's got a north pole up here and a south pole down there. And again, that looks a lot like the Earth spinning on its axis. And for the exact same reason that the Earth spins and these atoms spins, they create these little magnetic fields. All right, so in an NMR, what we do is we put all of these atoms that have an odd mass in our sample. We take them and we put them into a big magnet. So I'm just going to write this as a very big arrow. This is just a big magnetic field. Magnetic fields are labeled as B. So that's a big magnetic field, and all of these little guys line up. What we interpret for all of these little odd mass atoms is the environment that they're in. Sounds a little bit weird, but let's talk about, really quickly, what is an odd mass atom? So carbons have a mass of 12, so they don't have a spin associated with them. Hydrogens have a mass of 1, so they do have a spin. I'm going to draw out ethanol. Here we go. Oxygen has a mass of 16, so that would also not have a spin. So the only things that would have spins associated with them, and therefore little magnetic fields, would be these hydrogens. So all of these little hydrogens are all going to have little magnetic fields, and we're going to see all of those magnetic fields when we put them into an NMR magnet. Alright, sound good so far? When we put ethanol into this big magnet, those hydrogens, though, are more than just protons. They're more than just the nucleus of that atom. They also have that electron density around them. So remember that any molecule just kind of has electrons all the way around it. It's basically a big blob of electrons. That's a bunch of electrons. What the NMR does is it allows us to see the different amount of shielding around a nucleus. All right, which sounds very odd, but bear with me. Each of these little nuclei, right here, right here, right here, 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 and here, all of them have an odd mass, so they're all spinning in little tiny circles. So they are all generating little tiny magnetic fields. But they all have an electron cloud around their nuclei, and those electron clouds essentially interfere with that big magnetic field that they are experiencing due to the instrument. Therefore, what the NMR lets us see is the amount of electron density around those protons. The electron density acts like a little force field around those protons. So we see different environments, or we see different signals for the different amount of electron density around those protons. Let's look at these protons here. I've got 3 protons down here at the end that are approximately the same. I've got 2 protons in the center coming off of that carbon, and I've got 1 hydrogen over here to the right. So what we're actually going to see is three different signals because each of these hydrogens is going to experience a slightly different amount of electron density around them. And hopefully, based on what we know about chemistry and the periodic table already, you should be able to tell me why. So think about this. When we have hydrogens that are attached to oxygens, that oxygen is going to be pulling their electron density away because it's more electronegative than the hydrogen. So it pulls electron density away. And this hydrogen here has less electron density around it. So it has less shielding because those electrons essentially act like force field shields around those protons. On the other hand, if you look far to the left, these hydrogens that are way over to the left really have, the oxygen's a little too far away to matter. They've got nothing pulling their electrons away. Their electrons are evenly shared with the carbons that they're bonded to. Therefore, they have essentially a full dose of electrons around them. Therefore, these guys would be most shielded. They have the most electron density compared to the other hydrogens within this molecule. Because they have the most electron density, we would say that they are the most shielded. All right, these hydrogens right here, because the oxygen is pulling electron density away from that carbon, it's going to be pulling a little bit of electron density away from those hydrogens as well. Therefore, this guy will be somewhere in the middle. So we'll just say that this is somewhere in between. All right. When you put this molecule into an NMR, you would get a signal, or three different signals, on a spectrum that looks roughly like this. All right, the scale of this is ppm. We call this the chemical shift. And we label it with a little tiny delta. All right, delta means change. And we see this as a change from a standard that we put in. But on the far right side, we would have the more shielded protons. And on the left side, we would have the ones that are less shielded. So in this case, what we would see is the hydrogen that's way off to the left here, these guys over here, these guys are more shielded, so we would see them way over here. So we would see a peak that looks like this. The hydrogens that are, or the single hydrogen that is over here on the right attached to the oxygen, this guy has less shielding. It's having electrons pulled away by that oxygen. So this guy would appear furthest to the left because it is the least shielded proton. And then that other peak would be somewhere in between. And that's what we would see. So there are values on this, and we'll get to it in a second, but really what it lets us see when we put a sample into an NMR is the amount of magnetic field that these different hydrogens experience, and that has everything to do with the amount of electron density around them. So let's talk values. When we look at the NMR spectra, we have the most shielded protons all the way over to the right, and the least shielded protons all the way over to the left. So the most shielded protons are going to just be the hydrogens that are connected to carbon with nothing else going on around them. So these would be hydrogens like in a CH3, like these guys right here, or just in a CH2 with C's around them, or even a CH with all carbons around them. Those guys are going to be the most shielded because really they have nothing around them pulling electrons away. When we think of the periodic table, we think of every other atom that appears in organic chemistry. It's mostly oxygens, nitrogens, halogens, carbons, and hydrogens. Carbons and hydrogens are the only ones that share their electrons evenly. Everything else would pull electrons away and therefore de-shield or reduce the amount of shielding that those hydrogens feel. So the most shielded hydrogens would be those just attached to carbons with nothing else around them. These guys all appear in the region of approximately 1 to 1.5 ppm. The exact values are in your book, but I think I'd rather have you get a general idea of where these guys are showing up, not know exact specific values. So these guys show up on the region of about 1 to 1.5 ppm. And again, in lab we'll talk about what ppm means, but it's a measure, it's an indirect measure of how much shielding these guys feel. So those guys are way off to the right, and that's kind of where they show up. If you have something else next door, there's going to be something pulling electrons away from these carbons and away from the hydrogen. Anything that pulls electrons away from these hydrogens is going to reduce amount of electron shielding and therefore shift the peaks further and further to the left. All right, so in the region between about 2 and 2.5, we see a bunch of additional hydrogens showing up. So I'm going to say that this is the 2 to 2.5 region. We would have a CH right next to an alkene. So not attached to an alkene, not a hydrogen on an alkene, but a CH next to an alkene. We would have a CH next to a carbonyl, or a CH next to a benzene ring. I'm just going to write pH for phenyl ring. The other thing that we'll have here is an H directly at the end of an alkyne. We'll get to the details of why that is later, but all of these guys appear somewhere in between 2 and 2.5 ppm. You can't always tell exactly what that hydrogen is. That is to say, if you see one that shows up at 2.2 ppm, you're not really going to know if it's a CH next to an alkene, or a CH next to a carbonyl, or a CH next to a phenyl ring, or an H at the end of a triple bond. But you would know that information by combining this with something like IR that tells you whether you have an alkene, or a carbonyl, or an alkyne, or something like that. All right, moving on. In the 3 to 4 ppm region, we have hydrogens that are next to carbons, but that carbon is attached to a heteroatom, or something besides carbon. So an CH next to an O, or a CH next to an N, or a CH next to a halogen. Those guys show up somewhere in the region of about 3 to 4. I'm going to get a little bit cramped in here if I'm not careful, so I'm going to put in the next groups a little bit by themselves. What we see between 5 and 6 ppm are hydrogens that are directly attached to an alkene. So an H directly attached to a C double bond C. This H attached to a C double bond C is different from what we talked about over here. Over here between 2 and 2.5 we have an H on a C that's next to a C double bond C. So this hydrogen is not directly attached to the alkene. The hydrogen directly attached to an alkene shows up pretty well by itself in a region from about 5 to 6. In a region from about 7 to 8 ppm, we see hydrogens attached to benzene rings. Again, this is directly attached to a benzene ring. In the region from about 9 to 10 ppm, we see hydrogens that are at the end of an aldehyde. That is to say, a hydrogen directly attached to the carbon in a carbonyl. And the least shielded hydrogen of all would be the hydrogen of a carboxylic acid. Carboxylic acids are acids, meaning that that hydrogen essentially has no electron density of its own. So this would end up at the far left, usually in between 10 and 12 ppm. So that guy is really the least shielded of all. It really has the lowest amount of electron density. What you're seeing here, besides the very last one I just did, is that these are the most predictable location of protons has to do with hydrogens that are attached to carbons. Hydrogens directly attached to oxygens, like in alcohols, or directly attached to nitrogens, as in amines, are much less predictable, unfortunately. So I'm going to give you a range for those, which is that in an OH, hydrogen directly attached to an alcohol shows up somewhere in between 2 and 7 ppm. Usually it's further to the right, usually 2 to 5 if it's by itself, usually about 5 to 7 if it's on an OH that's on a phenyl ring, but it's a pretty big span. It goes from about 2 to 7 ppm. So those are really hard to tell. NHs as well are pretty tough to tell. NHs show up between about 1.5 and 4 ppm. So not quite as big of a span, but still a pretty big span for OHs and NHs. Really what NMR is mostly about, though, is being able to tell us what those hydrogens are and where they're located, the hydrogens that are on the main backbone of a carbon chain. So if you think back to mass spec. Mass spec tells us how big the molecule is roughly based on its mass, and it tells us also about some of the less common elements such as chlorine, sulfur, etc., etc. But it gives us a big picture, really not much else. With IR, we're looking at functional groups. That is to say, it tells us everything about carbonyls or benzene rings, etc., etc., etc. But what neither of those do is tell us about the location and environment of the carbon backbone. That is the strength of the NMR, as it tells us information about the carbon backbone. So the location of these peaks, this so-called chemical shift, is actually one of about 4 discrete things that you can learn by looking at an NMR spectra. It's the simplest, so it's what we're going to start with, but NMR, there's a lot to unpack, and that's why we split it up into 5 different lectures. Let's do some examples of specific molecules and talk about exactly where their hydrogens show up in the NMR. So let's go back to ethanol really quick. This is ethanol. CH3CH2OH. We said that the CH3s affected by nothing are going to show up between about 1 and 1.5, and indeed this guy shows up at 1.2 ppm. That's the CH3 that really has very little around it. A CH2, here we said a CH2 shows up between 1 and 1.5, except that a CH next to an O is going to be significantly de-shielded. It's going to have its electrons pulled away by the oxygen. So CHs next to O show up between 3 and 4. This guy shows up at about 3.6 ppm. The OH, on the other hand, we said we have really no idea. It's going to show up somewhere between about 2 and 7. And this hydrogen over here shows up around 5.3 ppm. And that's what we would see. That's where these guys would show up on that that spectra. So going from the right to the left, unfortunately our 0 is on the right. Again, we'll talk about why that is in lab. But we would see this peak over here, which I will call A, would show up furthest to the right. B, show up around 3.6, so somewhere in here. And then C, which would be the peak at 5.3, be over here somewhere. That's not exactly what the peaks would look like, but you get an idea of roughly what they look like compared to each other. So this would go from 0 left, this one would show up around 5.3 here. And that's roughly what an NMR looks like. Alright, let's do a couple more examples. If you just took the blank alkane of butane, which is CH3, CH2, CH2, CH3, it's not very exciting. There's actually only 2 different amounts of shielding. The ones furthest to the right and furthest to the left look exactly the same. They got the exact same stuff around them. So both of these guys show up around 0.9 ppm. The H's in the middle have a little bit more stuff around them, and kind of the more stuff you have around you, the further it shifts you to the left. These guys show up around 1.3. But all of these hydrogens are going to show up in the 1 to 1.3 or 1 to 1.5 region approximately. So they would be really close to each other. If this was our 0, these guys would show up really like this, kind of right next to each other. On the other hand, if you take the exact same butane chain and attach a bromine to one end, we would get 1 bromobutane. Now all of these hydrogens are going to look different because they're all going to have a different amount of stuff around them. The one furthest to the left isn't really going to feel any of the effect of that bromine. So this guy will still be at 0.9 ppm, just like the one above. In fact, these are exactly the same place. The hydrogen next to it is still too far away from the bromine to feel anything else. So that's going to be the exact same thing again. It's going to be around 1.3 ppm. Alright, going further to the right, the bromine doesn't show up, but these hydrogens would right here. These hydrogens are CHs next to a halogen. Just like the CHs next to an O that we saw up here, they show up in the 3 to 4 ppm region. Specifically, this guy shows up at 3.4 ppm. I wouldn't ask you to be able to tell me that, just that it shows up somewhere between 3 and 4. Alright, the CH next to that is going to feel a small effect of this bromine. So the bromine is strongly felt by the hydrogens next to it. It's weakly felt by the second carbon over. The second carbon over is going to experience a pull of down to about 1.7 ppm. And I'll give you kind of the way that I think about these. But this is what this guy would look like. I'll draw it out real quick. We would have a peak around 0.9, a 1.3, and a 1.7 all really close by, and then you'd see that 3.4 pretty far off a little bit by itself. Alright, so a way that I think about this is that a CH2 by itself would show up in between 1 and 1.5. If you put a halogen on it, or an oxygen or anything like that, what happens to that guy is that it experiences a pull that raises its chemical shift by about 2. So this guy has the effect of pulling that guy up by about 2. So we would say that if we put all that stuff together, that these hydrogens right here would show up between 3 and 3.5, because we're adding 2 to each side. So I don't try to memorize these in terms of where they show up, but what are the different effects that things have if they're next door? Let's look at another example really quick, which would be something like this. A CH, let's just do a CH3. CH3 shows up again between 1 and 1.5. If you put that guy next to a carbonyl, the carbonyl has an effect of bringing those hydrogens up by about +1. And that would mean that these hydrogens, instead of showing up between 1 and 1.5, they show up between 2 and 2.5, which is exactly what we saw on that chart. If you go back a couple slides, what you'll see is that those guys are kind of clustered together. We said that a hydrogen next to, or attached to a carbon next to a carbonyl, would show up, this guy would show up between 2 and 2.5. I'm just offering another way to interpret this. So if we use this kind of, instead of where do we expect them to show up, what effect do the neighboring functional groups have on them, we're better able to predict things like what would happen if you were next to 2 functional groups at the same time, because we're not going to bother putting that on a chart. So let's move all of this up. Let's look at what would happen if you were next to 2 functional groups. So let's consider a CH2 that has 2 chlorines next to it, one on each side. We said that a CH2 shows up between 1 and 1.5, and that a halogen has an effect of +2, but both of those halogens would have an effect of +2. And indeed, what we see in this molecule is that these hydrogens here would show up not at 1 to 1.5, and not 2 higher than that, but actually 4 higher than that, because you've got this effect on both sides of pulling it to the left or pulling it up by 4 ppm. So these hydrogens would overall show up somewhere between about 5 and 5.5 ppm. And you can do this if you're next to a carbonyl and a halogen, or 3 halogens, or anything like that. And it really is a good way to predict what's going on. So if you go back to that chart, what I would say is CHs show up between 1 and 1.5. Having them next to a halogen or a nitrogen or an oxygen gives you kind of a score of +2. Being next to that other stuff, a C double bond O or a C double bond C or a benzene ring, pulls you up by about 0.1. And beyond that, Know what 5 to 6 means, know what 7 to 8 means, know what 9 to 10 means, and know what 10 to 12 means. And you'll be in great shape for predicting chemical shifts for NMR. The last thing to add kind of goes back to where we were up here. I would say that we're usually talking about the score effect on this first carbon, or the hydrogens that are directly attached to whatever that functional group is. What about this guy that's a little bit further away? The first carbon really feels this score. It goes up by 2 if it's next to a halogen, goes up by 1 if it's right next to a carbonyl. But if you're 2 carbons away, you tend to feel about a quarter of that effect. So instead of going up 2, right? So these hydrogens go about 2 higher than normal. So instead of being 1 to 1.5, they show up between 3 and 3.5, which we see that in terms of the actual evidence of where it shows up on the spectrum. These guys show up about a quarter of that. So this guy is experiencing essentially a +2. This guy's experiencing about a quarter of that, or about a +0.5. So I would predict that this guy, instead of showing up between 1 and 1.5, which is normally where a CH is, it's between about 1.5 and 2, or half a point higher than normal. So there are a number of problems to try in the problems assigned, but what we're going to start off with first in class is I would like you guys to see if you can predict roughly where the hydrogens will show up in these 2 molecules. This one right here and this one right here. So write those guys down. Draw in your hydrogens, of course, and the first thing we'll talk about in class is where would we expect all of the hydrogens in those molecules to show up. Take care, and I'll see you soon.